This video is on section 6.1 notes, basic trig identities. So before we get started, I'm just going to go over what a trig identity is. A trig identity is a mathematical equation in trigonometry that is always true, regardless of the angle value used. So first we have some reciprocal identities. We have learned these before, well at least these three, and then these three kind of make sense. So we know that sine of alpha is the same as 1 over cosecant of alpha. We know that cos of alpha is the same as 1 over secant of alpha. And we know that tan of alpha is 1 over cotangent of alpha. And then the opposite is true for all of these. Cosecant is the same as 1 over sine, secant is the same as 1 over cos, and then cotangent is the same as 1 over tan. So these are identities that we've already learned about and know to be true. And then we have the quotient identities, where we knew from the unit circle that tan was y divided by x, and so that means that tan is sine over cos. Cotangent was x divided by y, and so that means that cotangent is cos over sine. So these are identities that we already know. We also learned one identity called the Pythagorean identity, which was that sine squared of alpha plus cos squared of alpha was equivalent to 1. And so what we're going to do next is look at two other Pythagorean identities, and we're going to look at where they come from. So it says we're going to find these alternate Pythagorean identities, the other two, by taking the original Pythagorean identity, which is sine squared alpha plus cos squared alpha equals 1, and we're going to divide it by sine alpha. So I'm going to divide the entire thing by sine alpha, which means that really I'm dividing all three terms by sine squared alpha. All right, so for this first term, I have sine squared divided by sine squared, and we know that anything divided by itself is just 1. So those cancel and leave a 1 in its place. Now for this one, we have cos squared over sine squared, and so what that means is we have cos alpha times cos alpha over sine alpha times sine alpha. And then for this one, we have 1 over sine squared, and so this really means 1 over sine alpha times sine alpha. Okay, so cos over sine we know is equivalent to cotangent. So this is a cotangent of alpha, and this is a cotangent of alpha. So we have 1 plus cotangent of alpha times cotangent of alpha. And then over here, we have a 1 over sine, and we have a 1 over sine. And so what we have here is a cosecant alpha, because 1 over sine is cosecant, times a cosecant alpha. So an alternative Pythagorean identity is 1 plus cotangent squared alpha equals cosecant squared alpha. So sine squared plus cos squared equals 1. We also have 1 plus cotangent squared equals cosecant squared. That's an alternate form of that original Pythagorean identity. We can do the same thing by taking the original Pythagorean identity of sine squared plus cos squared equals 1, and we'll go through and do the same process, but this time we're going to divide by cos squared. So cos squared, divide by cos squared, divide by cos squared. So I'm going to show a little bit less work this time since we know what's going to happen here. So sine squared over cos squared would be sine times sine over cos times cos, just like this. And we know that sine over cos gives us a tangent. And so sine squared over cos squared gives us tan squared. We know that cos squared over cos squared is just 1. and 1 over cos, and another 1 over cos, just like we had over here. Sine squared was 1 over sine, and another 1 over sine. That would give us a secant times a secant. And so this is going to give us secant squared. And so now we have 3 Pythagorean identities, and these are going to be nice to work with. So we have sine squared plus cos squared is 1, 1 plus cotangent squared equals cosecant squared, and tan squared plus 1 equals secant squared. Those 3 make up our Pythagorean identities. All right, so next we're going to look at how to simplify expressions that are written in trig. And so one of the things that makes this difficult for students is not that necessarily that it's in terms of trig, although it does look intimidating when you see it, and this is where students go like, oh my gosh, we've reached the point in math where we've lost all of our numbers, and that is true. But what usually messes with students is they forget that all the real rules of mathematics still apply. So if you have a fraction divided by a fraction, you still have to take the bottom fraction and multiply by its reciprocal. If you're adding 2 fractions, you still need a common denominator. If you have a sine plus sine, that's like terms, and that means you have 2 sines. If you have sine times sine, that means you have sine squared. So you have to think about the things that you've learned in math before and just apply them to trig. And if you don't know how to apply it to trig right away, then off to the side, use real numbers and try to do some math with those real numbers. Or try to use some variables and try to do something similar with the variables and make sure you understand how the math works before you just make up stuff to work with trig. So that's where students typically struggle here. So what we're going to do is we're going to simplify these, and we're going to do that by using all these equations, all these identities that we have up here. And so what we do is we just make substitutions. We take one thing, we substitute it out for another, and then we use what we know about math to simplify from there. Maybe we get a common denominator, maybe we add like terms, maybe we multiply 2 things together. We'll do things like that. So here it says tan divided by secant, and they already told us in the instructions that we should write everything in terms of sine and cosine. So I'm going to go up here. I know that secant can be rewritten as 1 over cos, and I know that tan can be rewritten as sine over cos. And so that's what I'm going to do. I'm rewriting the problem in terms of sine and cosine, and then I'm just going to use math to simplify. So tan is sine divided by cos. On the bottom, I have secant, which is 1 divided by cos. And you'll notice that whenever I write sine and cos, I always have something right here that's the angle. It's always sine of an angle, cos of an angle, cos of an angle. I can't just write sine. I can't literally write sine over cos. I have to have some sort of angle notation written in there for this to be correct. Okay, now for the simplifying piece, I just do what I know in math I'm allowed to do. And in math, I know that if I have a fraction divided by a fraction, I should take the bottom fraction and I should bring it up and multiply by the reciprocal. So I'm going to take this top fraction and I'm just going to rewrite it, sine x over cos x, and then I'm going to multiply by the reciprocal of the bottom, cos x over 1. Now I'm going to do something else that I know how to do in math. I know that if you have the same number on the top and the bottom, they cancel each other out, or you could say that they reduce. Multiplying by cos and dividing by cos, those are inverse operations, and they undo each other. So these 2 cancel out, and I'm left with sine x over 1. Sine on the top, 1 on the bottom, and I know that anytime I have a whole number written as a fraction, if it's written over 1, I don't really need the 1, and so this just becomes sine x. So I started by using some substitutions from my trig identities, and then from there I just did math, and I made sure to do math that I know is appropriate and I wasn't making anything up. I did what I know how to do from my previous math courses. All right, this next problem, we're using the same strategy. We're going to get everything in terms of sine and cosine. It has sine plus, and then it has two trig functions that are multiplied together. So the first trig function is already written as sine, so I'm going to leave that one. Cotangent can be rewritten as cos over sine. So I'm going to have cos over sine multiplied by cos. At this point, I've made my substitutions. I've put these in terms of sine and cos, which is what they asked me to do. And now I'm going to go ahead and simplify by using things that I know how to do in math. So for instance, I know that if I need to multiply a fraction times something else, it could be helpful to take this something else and write it as a fraction as well. And you do that by putting a 1 underneath it. So I'm going to put the 1 there. So I have sine for the first term. For my second term, I multiply the numerators and I multiply the denominators. That's how you multiply two fractions together. So cos times cos is cos squared in the numerator. In the denominator, I have sine times 1, which is just sine. Something else that I've learned how to do from math is that if I want to add two terms together and one of them is a fraction, I'm going to need to have a common denominator between these two terms. So I'm going to put this over 1. If this has a denominator of sine and this has a denominator of 1, then my common denominator would be sine. So to get the first term to have that common denominator, I'm going to have to multiply by the same thing on the top and the bottom, and I'm going to have to multiply by sine to get that common denominator. So I'm going to multiply by sine on the top. I'm going to multiply by sine on the bottom. So at this point, my first term is a fraction. Sine times sine is sine squared. I have sine on the bottom. And then my second term is cos squared over sine. I know in math that if I have the same denominator, I can write this as one fraction. So I'm going to write this as one fraction with a common denominator of sine. And then for the numerator, I'm just going to write sine squared plus cos squared. And it depends on how close you've been paying attention. If you've been kind of zoning out, you probably didn't see anything. If you haven't been zoning out, you might be thinking, wait a second, that's that Pythagorean identity. So if we go back up here, we know that sine squared plus cos squared just equals 1. And so now what we're going to do is we're going to take this and we're going to say sine squared plus cos squared is just equal to 1. So what we have is 1 over sine. And 1 over sine is one of our reciprocal identities. It is equal to cosecant. And so that's as far as we can go, cosecant. So we took our original expression and we just kept doing trig. We did trig substitutions, or we did math simplifications, and we got as far as we could go until it was just there was one thing left. And sometimes you'll get down to one trig function, which is what happened to us for both of these example problems. Sometimes you'll get down to just a number at the end. Maybe you'd get down to 2 trig functions, but what happens at the end is that you end up with something that's more simple than what you started with. All right, here's another problem. So again, we're still using those same instructions that tell us to turn everything into sine and cosine. So tan is sine over cos. So I'm going to say sine alpha over cos alpha. Cosecant is 1 over sine. And then we are dividing that by secant, which is 1 over cos. And you'll notice that for each of these trig functions, I always put my angle. I have to put my angle there. If I don't put it, technically I'm writing gibberish. It doesn't mean anything. Okay, so at this point, I've done my trig substitutions. So now I'm trying to do things that I know are appropriate to do mathematically. So things that would be fair for me to do mathematically might be looking in this top portion. I can see that the sign and the sign could cancel out. We have a sign in the numerator, a sign in the denominator. We know that multiplying by sign and dividing by sign are opposites, and so they cancel each other out. So now I can see that I have 1 over cos alpha divided by 1 over cos alpha. And so some people might immediately see this as you have a fraction divided by the same fraction. And some people see this and they say, well, cancel the top with the bottom, I just get 1 as my answer. And that's totally fine. At this point, we have enough information to say that the answer is 1. But if you don't feel very comfortable with that, if you say, well, I want to fix it so I don't have a fraction divided by a fraction, that's totally fine. We can say, let's take the top fraction and we'll multiply by the reciprocal of the bottom. So I'm going to flip the bottom up, and I get cos alpha over 1. And then you can see what happens. We get these coses canceling. So cos on the bottom, cos on the top, canceling. And whenever they cancel like that, they leave a 1 behind. So we have 1 on the top, 1 on the bottom, 1 on the top, 1 on the bottom. 1 multiplied by 1 is just 1. So you could have stopped here and said your answer was 1, or you could keep going and say that your answer is 1. All right, for these next type of problems, there's 2 ways that we can do them. We can do them by using a triangle, drawing a triangle in the correct quadrant, or we can use a trig identity. And what I'm going to do is present both ways to you, and then when you approach these problems on My Math Lab, you can do either method. The textbook is set up for you to only use trig identities, but I had already taught you about using the triangles. So if you want to use the triangles, that's totally fine. I think honestly they're about the same level of difficulty. It just kind of depends on how your brain feels about it. So let's go ahead and try it. We'll set it up both ways and then we can go from there. So first it says, given that tan of alpha is -2/3 and alpha is in quadrant 4, find the values of the remaining 5 trig functions at alpha. So I'm going to go ahead and draw a picture of this. They already told me that my answer was in quadrant 4, or that my alpha was in quadrant 4. So there's my triangle. And I know that for tangent, my sides are opposite over adjacent. So the opposite side is opposite of the angle. So here's opposite. The adjacent side is next to the angle. So there's adjacent. And I know I have to assign the negative to one of those sides. So from the center, this side goes to the right. From the center, the 2 goes down. So the 2 is the negative side. And remember, only the left and right sides and the up and down sides can have the negatives. The hypotenuse is always positive. So the hypotenuse is always positive. Okay, so to find the hypotenuse, because we're going to need the opposite, the adjacent, and the hypotenuse to find all of our trig ratios. To find the hypotenuse, we're just going to do the Pythagorean theorem. So 3 squared plus -2 squared equals r squared. They always used r because they were calling this like a radius of a unit circle. But you could use h if you wanted to. It doesn't really matter. So 9 and 4 gives us 13. And so the square root of 13 is the radius or the hypotenuse. So I'm going to label this as root 13. Okay, so from here I have all the information I need. I could go through and find all of my trig ratios. All right, if we were to do the same problem using trig identities, we would use one of the Pythagorean identities. And so the Pythagorean identity that would be the most helpful would be the one that has tan. And so I'm going to look back here. It is tan squared plus 1 equals secant squared. So I'm going to write this up here. Tan squared plus 1 equals secant squared. Okay, so I know that tan is negative 2/3. So I have negative 2/3 squared plus 1 equals secant squared. So this is going to help me find the ratio for secant. I'm plugging in tan, I'm going to get secant from this. So negative 2/3 squared would be negative 2/3 times negative 2/3, which gives me positive 4/9. Okay, and then that positive 4/9 I'm going to be adding 1 to. And if I add 1, I would say that's 9/9. And so this would be 13/9. And you can already see some similarities here. We just got that hypotenuse, right? We just got that 13. So now to find secant, instead of secant squared, I just need to square root both sides. And when you square root a fraction, you square root the top and the bottom. So this means that secant alpha is root 13 over 3. Now what we have to be careful of is we have to make sure which trig functions should be negative and which trig functions should be positive. And we didn't draw it in a triangle so that we know which of these three numbers is actually negative and which of them are positive. We're just going to do it based on quadrants. So I'm going to draw this. And if you remember, I want to say it was in 5.6. Maybe. I talked about all students talk constantly. All of the trig ratios are positive in quadrant 1. Sine is positive in quadrant 2, sine and cosecant. Tan is positive in quadrant 3, tan and cotangent. And cos is positive in quadrant 4, cos and secant. So if our picture is drawn in quadrant 4, if I don't even draw a picture, but if I know that what I'm doing is in quadrant 4, then I don't even have to draw anything. I just know automatically that my ratios for cos and secant have to be positive. Okay, so I'm going to go through and write down the trig ratios that I've got. I've got sine of alpha, cos of alpha, tan of alpha. I don't even have to write down, but I can. And then cosecant is the flipped version of sine, secant is the flipped version of cos, and cotangent is the flipped version of tangent. Okay, so secant is positive, and so we get root 13 over 3. And so I know that for cos, I'm going to have 3 over root 13. Cos is going to be 3 over root 13. And if this is cos, I'm going to have to fix that, right? I can't have a root 13 on the denominator. I need to rationalize it. So I'm going to multiply by root 13 on the top and root 13 on the bottom. So in the numerator, I have 3 root 13. In the denominator, I have 13. Okay, so, and what I do at this point, there are probably different methods. I honestly didn't even look at the textbook to see what they do from here. But what I like to do is write down what my opposite, adjacent, and hypotenuse are from this. I don't have to draw a triangle. I can just do it from my trig ratios. So tan was 2 over 3, so my opposite over adjacent, and then my hypotenuse is the third side, so that's root 13. Okay, So we have adjacent over hypotenuse, hypotenuse over adjacent. There's the cos and the secant. We knew that tan is -2/3 and cotangent is -3/2. And then we can do sine and cosecant opposite over hypotenuse. That would be 2 over √13, but we have to rationalize it. And so when I rationalize the denominator, I would get 2 √13 over 13. And then the flipped version of that would be √13 over 2. And if I look at quadrant 4, only cos and secant are positive in quadrant 4. So I have to have a negative in front of the sine and a negative in front of the cosecant in front of their ratios to make sure that my signs are correct. So sine, tan, cosecant, and cotangent are all negative. Cos and secant are positive. If I did this one, I spend the majority of my time setting up the drawing, and then from there, once the drawing is set up, I can just go ahead and do all my trig ratios using the sides. Okay, let's try another one. So this one says cotangent of alpha is in quadrant 2, and cotangent is negative. So quadrant 2, there's my alpha. Tangent is opposite over adjacent. So cotangent is adjacent over opposite. So adjacent over opposite, adjacent over opposite. And one of those has to be negative. So this side goes left, this side goes up. And so the left side is the negative side. And then I'm going to go ahead and do the Pythagorean theorem to find my hypotenuse. So 3 squared plus -1 squared equals the hypotenuse squared. 9 plus 1 is 10. And so the square root of 10 is the hypotenuse. Okay. So this is all ready to do the trig ratios. Over here, if we were to use our identities, we would look for the trig identity, the Pythagorean identity that has cotangent. So we would not use this one. We would use this one. So 1 plus cotangent squared equals cosecant squared. Okay, and so 1 plus cotangent squared equals cosecant squared. Okay, and so we have 1 plus -1/3 times -1/3 is +1/9. The 1 I can write as 9/9. And so when I add these together, that gives me 10/9. Okay, and so to solve for cosecant, I get √10/3. All students talk constantly, and we are in quadrant 2. So the ratios that are positive in quadrant 2 are sine and cosecant. So cosecant is positive. In the instructions, they told us all we need is sine and cos. And so I'm going to go ahead and find the reciprocal of this. So sine of alpha would be 3 over √10. And if I go ahead and rationalize that, that would be 3 √10 over 10. Okay. And then for cos, I have enough information at this point to write down the 3 sides. So opposite, adjacent, hypotenuse. So tangent was opposite over adjacent. That means cotangent is adjacent over opposite. So adjacent over opposite, that leaves root 10 as the hypotenuse. And so cos is adjacent over hypotenuse. Cos is 1 over root 10. And so cos alpha is 1 root 10 over 10. You don't have to put the 1. You can just write root 10 over 10. And if we're in quadrant 2, then cos has to be negative. Okay, so when you do these problems on MyMathLab, you are welcome to do it either way. If it were me, I'm going to be honest, I'd probably do the triangles. That way it makes a little bit more sense to me. But if you like the Pythagorean identity, you know, go ahead and use it. That's fine. Okay, so next we want to look at the even and odd identities. And you might remember this maybe from high school. You know, I taught Math 171, and I don't even remember if we went over this in Math 171. So if we did it very, very briefly. So here are some things that you might remember from a previous math course, but maybe not. A function is an even function if you can plug in negative x, and when you are done simplifying things, you just get back to the original function. Something you'll notice about these functions, x squared, y equals x squared is an example of an even function. One thing you'll notice about them is that they are symmetric over the y-axis. You can fold them in half vertically over the y-axis, and you'll see symmetry on both sides. A function is odd if you plug in negative x for all the x's in the function, and after you do all your mathematical simplifying, you end up with the negative version of the function. This is true for y equals x to the third. And you'll find with these functions that they have, it's not like folding symmetry, it's like spinning symmetry. If you were to put a pencil at the origin and spin them around, spin them 180 degrees, then you would see like, oh, it's symmetric about the origin. So when we look at sine and cos graphs, this one is sine, this one is cos. One of them is even, one of them is odd, and that means that with one of them, when you plug in a negative x, you just get the original function. One of them, when you plug in a negative x, you get the negative version of the original function. So here you can see that with the cos graph, if you were to fold the paper right over the y-axis, it would be the same on each side. So that means that this has symmetry over the y-axis, this graph is even. Okay, so what that means is that if we take the function of cos and we plug negative x into cos, then when we are done simplifying that, we're just going to get cos. No negative, we're just going to get cos. Okay, and you can prove that by looking at your unit circle. You can say cos of pi 6, cos of negative pi 6, they have the same output. Cos of 7 pi fourths, cos of negative 7 pi fourths, they have the same output. They have the same ratio. Okay, so you can test that if you want. Over here, if we want to look at the symmetry of sine, you would put your pencil right here in the middle on the origin, and you would take your paper and you would spin it 180 degrees, spin it, and you find like, oh, that looks the same. So this one has that rotational symmetry about the origin, and that means that sine is an odd function. And if you plug a negative x into sine, you get the negative version of the function. So what this means is if I look at sine of pi 6 and sine of negative pi 6, I'm going to find that they have opposite signs. One of them is going to be positive, one of them is going to be negative. If I look at sine of 2 pi thirds and sine of negative 2 pi thirds, they're going to have opposite signs. That's what I'll be noticing. Okay, so we found two of those relationships. We're going to go ahead and fill them in down here. So sine of a negative angle is the same as the negative version of sine. cos of a negative angle is the positive version of cos. Okay? Now, if we were to take the reciprocal identities, it would kind of make sense that if this was odd, its reciprocal is odd. Because if you take the reciprocal and you plug a negative into the reciprocal, you're going to end up getting 1 over negative sign, which is just the negative version of the fraction. And so if we get the negative version of the fraction, that means we got negative cosecant. Over here, if we take cos and we do the reciprocal function, 1 over cos of negative x, we just get 1 over cos. And so that's the positive fraction. And so that means that this is secant, and so if we plug a negative angle into secant, we're just going to get the positive version of secant. All right, with tan, we have to think it through a little bit more carefully. So if I think about taking tan and plugging in a negative x, what that means that I'm doing is I'm actually taking sine divided by cos, and I'm plugging a negative value into each of them. So that would be sine with a negative plugged in divided by cos with a negative plugged in. And so if I go ahead and simplify that, sine of negative x is just negative sine x. Cos of negative x is just positive cos x. And so what I end up with is sine over cos, which is tangent, with a negative in front of it. And so if I plug a negative into tan, I get the negative version of tan, which means that tan is also an odd function. And you can imagine doing the same thing for cotangent. If we were to do cotangent, we would just invert this. We would do cos divided by sine, and cos would be positive in the numerator, sine would be negative in the denominator, and we would end up with negative cotangent. And so these right here are the even and odd identities. So we're going to use these for the next couple of problems. So it says, go ahead and simplify the expression. So we're going to do what we did before on those other expressions, where we're going to make some trig substitutions. And then after we make the substitutions, then we'll go through and we'll do whatever math is appropriate to get the problem to be as simplified as possible. So first we have sine of negative x. Sine of negative x is negative sine x. Then we have cotangent of negative x, which is negative cotangent of x. And if we multiply these together, I know that the negatives are going to cancel out. Negative times negative, I know that that's going to give me a positive. Now, from here, there's not much more that I could do mathematically speaking. One term times another term, if they're not the same, is just like, it's like saying x times y, you just get xy. You don't do anything, right? So at this point, I'm going to try something else that I know from trig. I'm going to try another substitution. And I know that from my quotient identities, I know that cotangent is cos divided by sine. So now I'm going to do a substitution, and I'm going to take the cotangent out, and I'm going to replace it with cos over sine. And now I can go back to doing math, doing just whatever mathematically makes the most sense. So I have sine over here. I can think of this as the top of the fraction. I have sine on the bottom of a fraction, and I know that this can reduce. Sine divided by sine gives me 1. And so now I can just say, well, that's cos. So this expression simplified to be cos. All right, we've got one more here, and it uses one of those even and odd identities, so I'm going to leave this paper over here. Okay, so this problem we have two fractions, and the first thing I'm going to do is I'm going to handle this part right here that has this even and odd identity on it. So I'm going to rewrite that first fraction. Cos of negative theta. Cos of negative theta is just cos theta. So this is 1 plus cos theta. And then the second fraction does not have one of those even and odd identities, so I can just write this one out. So 1 minus cos theta. And from here to do simplifying, I'm just doing regular math. So I have two fractions. I want to add the two fractions together, but I don't have a common denominator. So what I need to do is get a common denominator between those two fractions. So 1 plus cos does not have a 1 minus cos. 1 minus cos does not have a 1 plus cos. So what I'm going to do is I'm going to take the first fraction and multiply it by 1 minus cos on the top and 1 minus cos on the bottom. And I'm going to take the fraction on the right and multiply it by 1 plus cos on the top and 1 plus cos on the bottom. And one thing that students often say to me when I'm doing problems like this is they say, it makes sense when you do it, but if I were to do it on my own, I would never know that that was what I should have done next. And my response to that is, the more we do these problems, then you can start to recognize what to do next. So now, if you see two denominators and see a 1 plus cos and a 1 minus cos, you can recognize that this is the next step. And that's the best way to do these problems, is to just pick up strategies and then save them for later. Know like, hey, that's something that I've done before. Now I'm going to pick that up and I'm going to use it on future problems. So when I go through problems and examples, try not to zone out, because you could be losing or missing strategies that are going to be helpful later on. Okay, so we need to figure out what our denominators are, and the denominators are 1 minus cos multiplied by 1 plus cos. So I don't want my paper to get too messy. I'm just going to go ahead and FOIL that. 1 minus cos and 1 plus cos. I'm going to FOIL it off to the side. And I know that I need to FOIL it because this is 2 terms multiplied by 2 terms, and mathematically that's what I should do. This is like if I had 1 minus x and 1 plus x and I was multiplying those together. Okay, so I've got 1 times 1 is 1. 1 times positive cos is positive cos. Negative cos times 1 is negative cos. And then negative cos times positive cos, negative times a positive is a negative, and cos times cos is cos squared. So the positive cos and the negative cos cancel out, and we end up with 1 minus cos squared. Okay, so this is the denominator for both of these fractions. So 1 minus cos squared, 1 minus cos squared. Okay, now I had 1 minus cos times 1, so that's just 1 minus cos. 1 times 1 plus cos, so that's just 1 plus cos. And so now with these two fractions, I have the same denominator. So I'm going to go ahead and combine them together. And I can go ahead and add these numerators together. So 1 plus 1 is 2, and a negative cos and a positive cos added together cancel each other out. So I just end up with 2 over 1 minus cos squared theta. Okay, now we have something that this is a new thing we're going to learn, and we're going to keep track of this because it's going to be kind of like a new form of an identity that's going to be beneficial for us to know. So one of the identities that we learned was that sine squared plus cos squared equals 1. Now, if you wanted to, you could rewrite this, and you could take the cos squared and you could subtract it over to the other side. And in doing that, you could isolate what sine squared was. You could say, if I want to know what sine squared is equivalent to, I could find out just by subtracting the cos squared to the other side. And I would find out that sine squared is equivalent to 1 minus cos squared. So this is another alternate form of one of the Pythagorean identities. And some people do the same for cos. They say if I wanted to know what cos squared was, I could just take the sine squared and I could subtract it over. So some people say, all right, cos squared is 1 minus sine squared. And these are two other versions of the original Pythagorean identity that end up showing up in problems every so often. So what happened here is I had 1 minus cos squared in the denominator, and I can now make a substitution. I can take the 1 minus cos squared out and replace it with the sine squared. So I have 2 over sine squared. And we know that sine squared is really just sine times sine. And we know that if we have sine on the bottom of a fraction, that's really just like saying 1 over sine, and that's like a cosecant. So the first 1 over sine is 1 cosecant, then we have another cosecant. So if we have a sine squared on the bottom, what we actually have is 2 cosecant squared. And that's what this one simplifies to be, 2 cosecant squared, because we had a sine squared on the bottom of the fraction. All right, one last problem. So I'm going to go back to the beginning of my notes. The beginning of my notes said, a trig identity is a mathematical equation in trig that is always true, regardless of the angle value used. It is always true. So here they said, show that sine of 2t equals 2 sine t is not an identity. Okay? So this note says showing that something is not true is a lot easier than showing that something is true. If this identity can be proven false for one angle, then the identity is false. Because like we said in the definition, that for this to be a true identity, it has to be true for every single angle that you use, no matter what the angle is. So if we want to prove it false, then we should be able to plug one angle in, make sure it doesn't work, and then we can say, yep, I proved it false. If we want to prove that it's true, it has to be true for every single angle possible. And that's a much bigger ask, okay? So we're going to show that this is not an identity. We're going to prove it false. And all we have to do is plug in one angle and make sure it does not work. So I'm just going to choose an angle. It doesn't matter what angle you choose. I'm going to use t is pi fourths. And I'm doing that because off the top of my head, I don't know, that's the first one I thought of. You can use pi fourths, you could use pi thirds, you could use 7 pi fourths, you could use 5 pi thirds, you could use 11 pi sixths. It really doesn't matter. So sine of 2 times pi fourths equals 2 times sine of pi fourths. We're trying to see if this is a true statement or not. So 2 times pi fourths would be 1/2, right? Pi fourths and another pi fourths is pi halves. So sine of pi halves. Okay, 2. And then sine of pi fourths, if I look at the unit circle and I look at pi fourths, the y-coordinate there is root 2 over 2. So 2 times root 2 over 2, well, the 2's just cancel, and we end up getting root 2. Okay, over here, sine of pi halves. I have to look at the unit circle and look at pi halves and look at the y-coordinate, and the y-coordinate is 1. And so I just proved this is not an identity because this is not true. This is false. So since it didn't work for one angle, then it can't work for all the angles, and that means it is not an identity.